Alright, so today's topic is diffusion and homogeneous reaction. So we're going to try to model steady state diffusion with homogeneous first order reaction. So let me tell you exactly what that means. Say you have some region here that is spherical, so this is our control volume, and you got some species B and you have some species A, and the A is diffusing into the region that contains B. Let's say we have some sort of reaction right now that is occurring like this, where you have the B present within here, and then as the A comes in, the A will be consumed. Okay, that's basically all you need to know at the start of the problem. So again, you've prepared some spherical region with species B just laying around in the region, and when species A enters that region, it will react with species B. The goal of today's lecture is we want to be able to model the concentration of species A within this region here. Okay, so how are we going to do this? Well, we've talked a little bit about strategy, and again, this is basically the algorithm that you're going to follow whenever you're solving a problem in transport phenomena. So step 0 was draw a picture. That I've already done, so let's get right ahead and start with the diffusion convection equation. And again, we're interested in species A, so we're going to write the diffusion convection equation in species A. So step 1, start with the diffusion convection equation. Let me scroll up just a little bit. Okay. So from the previous lectures, you should know by now, you should be rather familiar with this step. The diffusion convection equation simply looks like this. Okay, now we need to figure out what we're going to do with each of the terms in here, because remember the diffusion convection equation is a complicated partial differential equation that we need the assumptions to be able to simplify and solve. So the first one we're going to make is one we pretty much make every single time, and that's steady state. So even though there's a reaction occurring, we're assuming that overall the concentration per time will not change. The other assumption we're going to make for now is that the reaction that's occurring within this system here is going to be first order. Now, this, if you've taken kinetics, you might be like, well, it's probably not going to be first order, but again, we're not going to assume it's an elementary reaction. We're just going to say it's simply first order in A. So assume that the reaction that occurs within the region can be written like this. So the reaction rate will be equal to negative kCa. The order of the reaction is the exponent that's found above the C over here, and because it's first order, that exponent is going to be 1, so it's simply going to be C. This K is a rate constant, and the reason why this term is negative is, again, because A is a reactant. It's going to be consumed as it enters this spherical region here. Okay, so that handles that. Let's go on to step 2 of our algorithm. Now we want to write the total flux equation. Okay, so our total flux is going to be the convective flux is going to be equal to the diffusive flux plus the advective flux. So this is our general expression for the total flux of a species A. And we're using the definition with the mole fraction and the total flux located over here of all species. And what we're going to do is the same thing. We sort it up here and assuming it's a first order reaction, we're going to say, okay, let's ignore the advection and assume that the only mechanism for mass transport here is going to be diffusion. You'll see that even with these simplifications, these rather large simplifications, things will get very, very complicated further on out. So now the third step in our algorithm is to combine the first and second steps. So from the first one, we have this, which you saw briefly up above, and in the second step, well, we want to put this in here, but to do that, we need to handle this divergence over here. So if you remember from the lecture on spherical and cylindrical coordinates, you could look up the formula for the divergence of this on Wikipedia. This is the formula for spherical divergence if we assume it's one-dimensional and the movement is only happening in the r direction. So now we have an expression that's one dimensional. We could drop all this vector notation, and now we could substitute this in here. So NA is going to be equal to JA, and we could put that right in there. So that brings us to step 4. Now that we know NA equals JA, we're just going to put it right there into the equation. We could use Fick's first law to express JA in terms of concentration as well as our coordinate system. So again, typically in Fick's first law you have a gradient, but we're going to be working in one-dimensional spherical coordinates, so that gradient will simplify to this. And now we're going to combine Fick's first law with the definition n equals JA, put it in here, and this is the expression or the equation we're looking for that models our situation so far. At this point, we usually do a little bit of cleanup, so we want to rearrange the equations that all the constants are in places that make the most sense. So what I'm going to do is I'm going to say, okay, both these terms are negative, so I'm going to multiply by -1, and I'm going to move this d out because it's constant. I'm going to move it over to this term over here. So I'm going to divide by d, multiply by -1, and this is pretty much what we're stuck with. The only other thing you could do is say, okay, we have the derivative of this, which is this times this. We could use the product rule and say that it's going to be equal to this. So again, hold this constant, take the derivative of this, add this, hold this constant, take the derivative of this. So we use the product rule, and this is pretty much as good as we could get for simplifying at this point. So, well, I guess there's one more thing we could do. We could bring this 1 over r squared into here, so we could distribute that, and this will be the differential equation that we need to solve to find the concentration profile of our system. So now this is where the problem is no longer a mass transfer or transport phenomena problem. At this point, it's going to be a math problem. So if you're not interested in the exact nitty-gritty details of solving this, fast forward in the lecture. If your class requires you to know the exact methodology for solving this, then keep watching. Okay, so now we need to figure out how to solve the ODE. So as usual, this is the part that's less interesting because it just involves a bunch of tricks that you need to know. So the first trick that we're going to use is we're going to make the equation that we're using here dimensionless. So let's introduce new dimensionless variables. The dimensions that we have in here are radius, which is in meters, and we have concentration, which is in moles per meter cubed. We also have this d in here and this k in here, but we're not going to worry about that right now. As long as we make the variables, the dependent variables, dimensionless, we should be able to make dimensionless groups out of everything else that is present. So I'm going to introduce a dimensionless radius that is going to be r over big R, and I'm going to introduce a dimensionless concentration, which is going to be C over CS. Perhaps that requires a little bit of explanation. So in this region here, R is centered about this point. Big R is going to be at the boundary of this control volume, and where big R is, we are also going to have CS, where CS just means the concentration at the surface of this control volume. So we're sort of introducing boundaries here when we make our dimensionless variables. So at this point, again, we introduce these dimensionless variables, and now because they're a little more useful to have in this form, I'm going to leave this up here, because this will allow us to directly substitute in this whenever we see R or C in our equation. So now we look back at the previous equation we had. I dropped the A notation just because it's going to get very messy soon, but the next step is going to be incorporating these two dimensionless variables, R bar and C bar, into this equation. So the kind of trick way of doing it is literally just substitute these in. What you need to be careful about is you can't do the d squared c dr squared. You need to make it d dr of dc dr. Hopefully that made sense. But once you've done that, then you could literally substitute in r bar big R and c bar cs wherever you see little r and c. The formal way of showing this is to actually use the chain rule but that takes like pages of work. So this simplification is fine, it'll suffice for now. The next thing you could do is, since these are differentials, C sub s and big R are constants, so you could pull them out wherever you see them. So over here, both these big R's are going to come out, you're going to get an R squared. This CS will come out over here, and you'll get a CS. Over here, another two big R's will come out over here, a CS will come out over here, and over here, nothing really happens. And now all of our derivatives are in terms of our dimensionless variables C bar and R bar. At this point, you can move all the constants over to the last term. So we're going to divide by CS and multiply by R squared. So this last term over here, since we divide by CS, this one is going to go away. And now there's going to be an R squared over here. And now the reason we did this is because we could put this in a form that's solvable if you've taken a differential equations class. So now let's look at the trick for solving the ODE. The trick comes from a very clever U substitution that again only makes sense because someone thought about it for a while and this was the only way to get a quick solution. So the U substitution is let it be the product of our dimensionless variables C bar and R bar, and this is just algebraically rearranging them. Now it gets a little bit, again, you'll just have to go through it for a while. So if we take the derivative of this U substitution with respect to R bar, then we have to use the product rule again. So take the derivative of this, leave that constant, and then take the derivative of R bar, leaving C bar alone. And to get the second derivative, again, it'll seem arbitrary right now. We need to again use the product rule, so we use the product rule here. That gives you these two terms. And then lastly, since it's a linear operator, we also just take the R derivative of this. As it turns out, you could group those two DC GRs together to get this. And then, again, it'll seem arbitrary, but if you divide by R bar or multiply both sides by 1 over R bar, you'll get this expression. Okay, so you're probably like, that was pretty arbitrary. Why did we do that? Well, what it does is it allows us to combine these two over here. So this over here, again, is our dimensionless equation, our ODE that we're trying to solve, and this is the U substitution that you just came up with. So these are the terms that are in common. So you could literally substitute the second derivative of U with respect to R bar in there, and this is what you get. Now you need to move that R bar up, so multiply everything by R bar, and you'll see that it's hanging out over here in this term now. Now if you remember our definition of the U substitution, U was C bar times R bar. So now this will turn into U, and now this, you have essentially U double prime plus some constant times U, which will either be significant to you or probably not significant to you. But this is in a form that you should have been able to solve in your Calc 4 or differential equations class. So at this point, go open a differential equations textbook and solve this. What you'll get is this as your general solution. And this also looks like a nightmare. So it's going to be hyperbolic cosines and hyperbolic sines. Okay, fantastic, right? This should also have a, should be over R bar. Yeah, so you got hyperbolic cosine, hyperbolic sine, and you got a linear combination of those two. So again, this general equation is just something you're going to have to see from revisiting your differential equations class. At this point, we introduce a new dimensionless, well, I don't know, well, it should be dimensionless. But we introduce a new variable that we're going to refer to from now on as the Thiele modulus, which is an important group. And it's simply going to take the form of these two constants that are located within your hyperbolic trig functions. Subbing that in, we get a slightly simpler general solution that looks like this. That is a function of our dimensionless radius and our dimensionless concentration. Okay, so by now you're probably just like, this is terrible, there's hyperbolic trig identities in there, like I've never used those before. Calm down, it's not as bad as it looks. Again, there's a lot of scary math in transport phenomena, but we will get through it. So step 6 in our algorithm is to define our boundary conditions. So for that to make sense, let's visit briefly what those hyperbolic trig functions look like. So hyperbolic sine is e to the x minus e to the negative x over 2, and cosine just has that minus sign flipped over to a positive. Again, this will seem arbitrary, but if you take these functions evaluated at 0, what you'll see is that e to the 0 is of course 1, e to the negative 0 is also 1, so 1 minus 1 is going to be 0, and over here 1 plus 1 is going to be 2, divided by 2 equals 1. So why do we care about these two trig functions evaluated at 0? Well, let's think a little bit about what's going on in our system. So again, we had this as our initial setup. Right, this is our control volume. We have the particles of A entering and the particles of B ready to react with them. At the center of our coordinate system, this is r equals 0, and this is r equals big R. Now remember, since we defined our dimensionless variables like this, when this is at 0, our bar is also going to be 0, okay? So we pretty much can't avoid the fact that this is going to be a boundary. Similarly, when you're at the edge of the system, r is going to be big R, so big R over big R is simply going to be 1. So r bar is going to range from 0 to 1, and similarly, c bar is going to be, well, we'll talk a little bit about c bar in a bit. It's a little bit more complicated. So anyway, if we take our solution, remember this is our generalized solution, and we try to evaluate it at the center of our coordinate system. So we basically put zeros wherever you see r bar, you see that we might have a huge problem. Remember, we just above evaluated hyperbolic sine and hyperbolic cosine when there's 0, and what we find is that for the cosine you're going to get 1, and for the sine you're going to get 0. So this 0 on the bottom is okay because it's got this 0 over here, this term will go to 0. That's fine. But over here, since this is 1, this term will actually blow up to infinity at r equals 0. But we know that that doesn't really make sense, right? We want our concentration to be finite. It doesn't make sense for our concentration to be infinite. So we're forced to conclude that for our first boundary condition, since we require concentration to be finite at the center of our coordinate system, we must accept the fact that k sub 0, that constant, must be 0, and that this is our general solution now. Okay, so how do we find the other constant k1? Well, we know our boundary condition is going to be at the edge of the system. So when we're at the edge of our control volume, we're going to have some concentration. And if we look at the dimensionless groups that we made, or the dimensionless variables, that's going to be 1 for r bar and 1 for c bar. Subbing that in, put in a 1 here, put in a 1 here, and we'll find that k sub 1 is just going to be 1 over the hyperbolic sine of our Thiele modulus. What this tells us is that our final concentration profile is going to look like this. So c bar, our dimensionless concentration, is related to our dimensionless radius by hyperbolic sine times Thiele modulus in the r bar over some initial Thiele modulus, which is a constant, so it's not that bad. Alright, so what is actually going on? I'm going to try to explain. So this plot over here is dimensionless r versus dimensionless c. So I basically took this and I plotted it. The only thing I changed was the Tm, which was the Thiele modulus. What you see is that when the Thiele modulus is 1, your concentration profile looks like this. When it's 5, your concentration profile looks like this. And when it's 10, your concentration profile looks like this. And you could think of it like this is your spherical region. This is the center point. And then what this graph is telling you is that as you move away from the center point, what is your concentration? So for instance, this says that your concentration at the center at r bar equals 0 is relatively close to your concentration at the surface. But over here, when your Thiele modulus is very large, you basically have no concentration at your center, and then at your surface, you have a substantial concentration, depending on what your C sub S value is. So remember, these are dimensionless groups, or dimensionless variables, rather. So remember also that we're looking at the concentration of A. So if the concentration of A is high at the surface, and as you get further and further in our spherical region, it drops, that means the A is being consumed by the B that is present there as that reaction happens. So in turn, what it means is that when your Thiele modulus is small, A is able to get decently far into the region without reacting. That's what you see up here. A is present at the center of our region, which means A was able to get into the control volume and get all the way to the center without entirely being consumed by B. On the other hand, if your Thiele modulus is large, it means A was able to react somewhere close to the surface, or it just wasn't able to get further enough into the control volume. So the A was consumed before it got to the center point. That's why you see incredibly low values of A over here when the Thiele modulus is large. Let's explore a little bit more about what is happening, because it's interesting, and it's more interesting than the actual mathematics of the solution per se. So this will be a lot of information at once. So what we have over here is that I have varied the size of our control volume, so the size of our spherical region, essentially. This red is just B that is present within the region. Assume that it is a uniform concentration, even though it might not exactly look like that. But basically, this is a small spherical volume, this is a larger spherical volume, and this is a very large spherical volume. What's happening is that, and they're color-coded, in this blue one, we have a small volume, right? So our R squared volume is small. What that means is our Thiele modulus is small. So the small particle, or the small spherical volume, corresponds to this up here. Because it's small, the chance of A being able to get further into the region is rather easy, right? It doesn't need to move that far into the region to be able to get to the center. But when you increase the spherical volume size, A needs to move further into the region to be able to get to the center, which is located over here. And that's actually pretty difficult, right? Because there's so much B in the way, the chance of A getting to the center without reacting is pretty small. When you have an incredibly large particle size, the chance of A getting to the center is almost impossible. That's why you see the values drop off so fast over here in this plot. As it gets further and further in, there's less and less A that is able to make it to the center. So what you're getting here is you're saying that as you increase the control volume size, as you increase this R over here in the Thiele modulus is going to get greater, and when the Thiele modulus is greater, the species A that is reacting won't be able to get as far into the control volume. It won't be able to get to the center of the control volume. Okay, let's look at another trend. This time we are going to be looking at diffusivity. So we're going to hold particle size constant, or control volume constant rather, and it's all going to be the same size. Remember, this B in here is of uniform concentration, and here we have three separate species once again. This light blue one over here represents a species that has a very high diffusivity. Remember, that means it has a very good ability to diffuse or move past other particles. So if it has a very high diffusivity, it has a very high chance of making it further along into this control volume because it's able to slip past or move very quickly into this region. There's less chance for molecules of B to grab onto it and react. If you make the particle very slow moving, very hard to diffuse, then it's basically spending more time trying to get to the center, and it has more chances to react with particle B that is located in there. So the trend you're seeing over here is that as your diffusivity is high over here, your Thiele modulus is going to go down. When your Thiele modulus goes down, it means that A is going to be able to get further along into the control volume, which is why you see this plot, this blue one with a high diffusivity up here. It was able to get far along and retain high concentration further into the control volume. Lastly, just a comment here, because this is a transport phenomena class, not necessarily a kinetics class. The higher the reaction rate you have, the larger the Thiele modulus that you'll have is, and it'll pretty much follow the same pattern as with the particle size. It won't be able to get as far into the region because its chances of reacting are going to increase, because the reaction rate will be fast. The more time it spends in that control volume, just the higher chance it has of undergoing the reaction. So it won't be able to get that far in there. That's why sometimes you see people express the Thiele modulus as a ratio of reaction rate to diffusion over here. But again, that's more of a kinetics topic to discuss. So the takeaways: know what a Thiele modulus is, know how it corresponds to the physical significance. The actual concentration profile isn't that important, but the basic assumptions that we used to arrive at the ODE is what's the takeaway here. Solving the ODE isn't really that enlightening, so I wouldn't focus too much on that.